All right, so in this video, we're going to check out vector projections and particularly come up with a formula, look at how we can derive a formula to find the projection of one vector, in this case v, onto another vector, in this case w. So what we're going to start with is, first of all, this is the formula that we're going to ultimately end up looking at. So the projection of v onto w. This is the notation, first of all. And the formula for this, we can actually find that projection using the formula v dot w over the magnitude of w squared multiplied by the vector that's being projected onto, in this case w. All right, so before we get into the proof, let's just kind of look at what we're dealing with here. The projection of the general process to find the projection of v onto w is we're going to take the vector that's being projected onto, so in this case w, and we're going to shrink it down to a unit vector. So we know that the unit vector of w can be found by taking 1 over the magnitude of w and then multiplying it by whatever w is. So in other words, we're going to take each component, the x and the y component of w, and we're going to divide it by whatever the magnitude of w is. And that actually gives us a vector in the same direction as w that has a magnitude of 1. So that's the first part, is we take w, we shrink it down, and then after that we're going to figure out what we have to multiply that back out to in order to get the actual projection of v onto w. So we're going to multiply this vector by some scalar, this unit vector, in the same direction as w by some scalar. So in general, this projection of v onto w can be found by figuring out what that scalar is and then multiplying it by the unit vector in the same direction as w. So this is what we're going to use to start off our proof. We've got our let statement up here, and so the proof is going to essentially follow by manipulating this equation right here. So my proof, we know that the projection of v onto w can be found by figuring out what that scalar is. So it can be found using the scalar, taking some scalar and multiplying it by the unit vector in the same direction as w. And we should probably specify exactly what a is, where a is a scalar multiple. All right, so really the derivation comes from this, comes from knowing what these particular components are. So first things first, we've got our projection here. We've got a vector v and a vector w. And when we look at the projection, we know that this angle theta is the angle between v and w. There's v, there's w, and theta is that angle. Our scalar is going to be a. And so we need to take the unit vector of w, shrink it down, and then multiply it by that scalar in order to get the projection of v onto w, which is going to look something like this. All right, so let's just take these two expressions and figure out what we know about them. I know that based on a right triangle trig, this is a right triangle here. So based on a right triangle trig, I know that the cosine of theta is going to be equal to the adjacent side, which is my scalar, over the magnitude of v. And that's just adjacent over the hypotenuse. So our manipulating this a little bit, solving for a, I know that a is equal to the magnitude of v times the cosine of theta. So I can use that and plug it right back up in here. So put A times the unit vector of W is equal to, we know an expression for A, so it's just a magnitude of V times the cosine of theta. And that comes directly from down here. And then the second part of this is we know how to find the unit vector. The unit vector in the direction of W we can find by taking W and multiplying it by 1 over the magnitude. So I've got 1 over the magnitude of W multiplied by W. All right, so the next piece of this is we know an expression for the cosine of theta. We know that the cosine of theta is also equal to the dot product of V and W over the magnitude of V times the magnitude of W. So let's go ahead and substitute that piece in. So we've got V dot W over the magnitude of V times the magnitude of W. And that's for the cosine of theta. Everything else gets brought down. So this is substituting for cosine of theta. Let's move some stuff over here. We get this expression. And so now it's really just a matter of simplifying. We've got the magnitude of V in the numerator and both the denominator. So that's gone there. So simplifying. We have our magnitude of V's are gone. I'm still left with a V dot W in the numerator. In the denominator, I've got the magnitude of W times the magnitude of W, which is the magnitude of W squared. And now I've got W left on the outside, and we're done. So wrapping this all up, we need a therefore statement for our proof. So therefore, the projection of V onto W is given by this equation here. V dot W over the magnitude of W squared times vector W.